Good evening all. Welcome to the fourth session of NPTEL live sessions for Engineering Thermodynamics course. So I am Durga Prasad. So this week we will be discussing on pure substances and how to evaluate the properties and a few more examples of mixture of gases. So before starting the session, we'll wait for a couple of minutes for a few more students to join. I'll share my screen in the meantime. Okay, I guess we'll get started. So just give me a second. I'll just open the Steam tables that we are going to be using today. So I'll go through how to go through these tables as well. We will look at that problem as well. So but before that, let's get started. So the first question is, you have a rigid container, a closed rigid container of a certain specific volume. It's specified that the volume is 0.5 meter cube, is placed on a hot plate. Initially the container holds a two-phase mixture. So by two-phase mixture we mean it is in equilibrium with the liquid phase is in equilibrium with the vapor and saturated water vapor at a pressure of 1 bar with a quality of 0.5. So quality is defined by what is quality? The quality here refers to the mass of vapor divided by mass of liquid plus vapor. So it is given that you also call this as the rarefaction or vaporaction of that particular two-phase mixture. So now what is happening here? After heating, the pressure in the container is P2 equal to 1.4 bar. Since it's a closed container, as you are giving the heat gets since it's a closed container, the volume remains constant, so the net work done will be 0. The heat, so from first law we have that whatever heat that is given as input should be converted into internal energy. So it will increase the pressure as well as the temperature inside the container. So now there are two things. In order to fix the state, you need to know at least one of the properties. So it is specified here that the final pressure is 1.5 bar. So at 1.5 bar, what is the temperature? That's the first question. The next one asks you to, at this final stage, what will be the mass of vapor present in the container? And third thing, they ask you that if the heating continues, so if you keep on heating that particular mixture, determine the pressure in bar when the container holds only saturated vapor. So it's, imagine you have a vessel that is filled with water, like not completely filled but half filled with water, and then you are gradually heating it by closing the vessel with a lid. Now as you keep on heating, what would happen? The water starts converting into vapor, and then eventually if the particular container with the lid can hold sufficient pressure enough, eventually the entire liquid inside will get converted into vapor and you will be left only with vapor. So in that particular stage, if suppose the entire container is filled only with vapor, what would be the final pressure? So that would be what you would be required to find. So how do you proceed with such problems? So the first one is to find the temperature at each stage. So let's split part by part. So what are the different stages initial stage, do we know the temperature? Initially it is before heating, and then there are 3 stages. So let me define stage by stage. There are 3 stages. So stage 1 is the initial one without heating. Stage 2 is basically heating till pressure is 1.5 bar, and stage 3 is when only saturated vapor is left. So these are the 3 stages that we are left with. So so we need to find the temperature in each of these stages. So for the first stage, how do I find the temperature? So what are the properties that I know here? I know what is my initial pressure. Initial pressure is given as 1 bar, and I know the quality. Quality is the dryness fraction as 0.5. Using these 2 information, can I find the temperature? So in order to do that, you need to know how these properties are related. First thing, you cannot use ideal gas law. Ideal gas law should be used only in either inside the dome, or basically when you have 2 phase mixtures. And you can use ideal gas law only in the supersaturated region. That is when the temperature is so high that you will be only in the vapor stage. But now you have both liquid plus vapor, so in such scenarios you should not be using ideal gas law. So how do I go ahead with that problem? That is when people have done some experiments and they have come up with some tables. So I'll show you a glance of some table here. How does it look like? So these are the saturated water. So if you see the curve of the 2-phase curve, you will have a liquid vapor line, and this is that particular saturated water table. Temperature, like you have 2 different tables. You have a temperature table and then you have a pressure table. So in the temperature table, here is your saturation temperature and correspondingly that particular pressure. This is the liquid vapor. This is the specific volume for the liquid one, and this is when it is completely saturated, and this is for the saturated vapor. Similarly, you have internal energy, enthalpy. We will come to entropy little later. So this is one table. Otherwise, in most scenarios, like in the present example, you are given pressure. A pressure of 1.5 bar as well as, so it is given a pressure is 1 bar, and the vapor fraction, I am just denoting with x, is given as 0.5. So instead of temperature, pressure is given. There are 2 ways. You can either use the temperature table and then identify that point where the pressure is 1 bar. So it will be somewhere close to this one, somewhere between 95 and 100. The pressure is going to be somewhere between 95 and 100 and more close to 100. Or there are other tables that are provided only in terms of pressure. This is another table that you can use. So in this table, you can directly look up for the pressure and see what is the saturated temperature. That is the temperature that particular 2-phase mixture is going to be. So if you observe this, the temperature is going to be constant inside the dome region when pressure is also constant. So both the phases coexist together at the same pressure as well as the same temperature. So here at 1 bar pressure, we have saturated temperature 29.63. So now this temperature is not going to be dependent on the vapor fraction. Only the specific volume, internal energy and enthalpy are going to change with your vapor fraction. So I've just taken the values directly from the table. So this is my initial temperature, my VF1 or is the liquid vapor. This is for the liquid stage, saturated liquid state, and this is for the saturated vapor state. So I have these values. So in order to calculate the specific volume at a different value, all I have to do is initial one plus the vapor fraction times Vg minus Vf. You can also similarly do for the other properties, like for example, you can write the internal energy at this particular state as the internal energy in the liquid state. I'll just write only as the liquid state or saturated liquid state plus the vapor fraction times saturated vapor state minus saturated liquid state. Similarly for enthalpy, entropy, whatever other properties that you want to calculate. So after heating, what is happening? After heating, the final pressure is given as 1.5 bar. Now at this 1.5 bar, your volume is anyway remaining constant because it's a closed container and it's a rigid container and it's a closed, and we are considering that no mass is escaping from the system, so it is a closed, since it's a closed system. So what do we have here? We have volume constant and mass constant, so the specific volume also remains constant. So the final specific volume will be same as the initial specific volume. We have already calculated the initial specific volume as 0.8475 to whatever the value that is over here, and the specific volume in this particular state is also going to be the same. But now we have to find what is the value of temperature at this particular stage. So how do I calculate that? So after heating, we know only the pressure. We do not know the vapor fraction. Like we said, in order to locate any point inside the dome, you need to need at least two independent properties. Pressure is 1.5 bar. Now I know specific volume as 0.8. Now if I go to the steam tables at 1.5 bar, this is my liquid and this is my saturated vapor stage. The saturated vapor, if you see the specific volume for the saturated vapor, it is around 1.159. So Vg2 is 1.159. So from there I have the Vf and V2, Vg. So from there I can directly calculate the vapor fraction, so which is given as if you just substitute these values. Yeah, if you just calculate the value of vapor fraction, it's coming to around 0.73, and since it is less than 1, vapor fraction has to be between 0 and 1, which is happening here. So which means you are still in the dome, so you have a two-phase mixture of liquid plus vapor, and that is coming to around this one. So we know that the final pressure is 1.5 bar, so at 1.5 bar, whatever is the saturated temperature, that will be the temperature here. So if you see the table, the temperature is around 111.4 degrees Celsius. So this is straightforward. Now the next part of the question asks you to find the mass of water vapor. So how do I calculate the mass? I know the initial volume, I know the specific volume of the gas, so I can directly calculate the mass. Like the vapor fraction is defined by mass of vapor plus liquid plus vapor, and I know the total volume. So liquid plus vapor can be written as V by specific volume. So if I just multiply with the vapor fraction with the corresponding specific volume, like volume divided by specific volume, I will be able to directly get the mass of vapor. So you see, as the heating is happening, the liquid is getting converted into vapor, since the mass of vapor is actually increasing like from 0.29 to 0.43. Now if the heating is continued further till all of the liquid is converted into vapor, which means your vapor fraction is going to be, when all of the liquid is converted to vapor, the vapor fraction is going to be 1. So in that scenario, we have x3 as 1, but the specific volume should remain the constant, because the volume and mass are constant. Since it is a rigid container, volume is not increasing, and it is a closed container, so the mass is also constant. So your specific volume remains constant, so V3 equals to V2. So I have my V3, which is equal to V2 and which is equal to V1. So my volume is there. So now what do I need to do? I don't know the pressure, I don't know the temperature, but I know that it is going to be in some superheated state. So how do I determine my final pressure? So now comes the next part of the tables. So we know for sure that it is going to be in a superheated region. So we need to look up data for that. So if you happen to see, so what will be the pressure at which this is going to happen? So let's take the steam tables and let's see when it is only saturated vapor, if it is not in superheated state. So you have this values here. So this is between 0.8857 and this is some 0.7187. We need the value to be something close to 0.84. So I've just taken two different pressures, and then we use a linear interpolation between these two pressures to determine the appropriate pressure. Now if you just do a linear combination, so pressure at this particular point is going to be 2 plus the linear interpolation of these values, which will give you a value of around 2.11 bar. So what if after reaching this only saturated vapor state, if you keep on heating further, what would happen then? If you keep on heating further, what would happen is, again, most of this saturated vapor now will get converted into superheated state. Now if I need to find the pressure and temperature in the superheated state, that would be not possible, because again I would need two independent properties, and this information is not going to be useful for me anymore. This x3 equal to 1 is useful for me now as long as I am on the saturation curve. This tells me that I am on the saturation curve. So when I am on the saturation curve, I need only one independent property. By fixing the pressure, I will be able to fix a specific volume. By fixing the specific volume, I will be able to fix the pressure and temperature, other things. So knowing specific volume alone is sufficient to tell me what the pressure is, only if I am on the saturation curve. This is not happening if you are in the superheated region. So if I am in superheated region, then the question needs to tell me that if this is the pressure, what will be the temperature? Or let's say, if in the superheated region, if your pressure is 2.5 bar, so what would be the corresponding temperature? If suppose if question is asked in such a way. So I'm just adding a little part to the next question. Let's say we have the next part as D, where the question asks you if heating continues further till the pressure raises say 2.5 bar, what will be the final temperature? So how do you go forward in such a case? So the next thing is, now you need to come up with another table. These tables will only give you the on the saturation curves. Now I need to know something in the superheated region. There are two ways to go about it. Now one way is, you know that in superheated region you can follow the ideal gas law. So basically I can go about it in two ways. Use superheated tables or approximate with ideal gas law. So I will be taking, we'll look at both of these approaches. So if you want to go to the superheated tables, you can just look at them. I'll have you. So this is for a superheated water vapor table. So all it has is, it just has only two properties. Now we don't have vapor fraction coming into picture. So all you need to know is see the corresponding pressure and how it varies with temperature. This is the specific volume, internal energy, enthalpy and entropy. So at this particular point, you know the final pressure is 2.5 bar. So you just look up at that particular value. So in here only 1.5 and 3 are there. So you can do some linear interpolation to find the approximate value between them. But in order to fix the state, now the pressure is known. I need to find the temperature. So how do I find the right temperature? So which means you need to know some other property, that is a specific volume. So out of these specific volume, you choose that specific volume which is close to the value that you need. The value I would be requiring is 0.847. So you just pick up the value close to that. So that is something close to this. So your temperature will be close to 280 degrees Celsius. Like you need to do a linear interpolation between these two values to get the corresponding right value. We will also take up a problem on that. But for now we can just approximate with an ideal gas. So in case of an ideal gas, we know that this is a constant volume process. So so P is proportional to T. So I'll directly assume that the final pressure, by like we already know the final pressure, so we will take up that way. We already know the initial pressure, so let's say P4. So this comes out as so in here we know the value of T4 and 2. We know the value of P4 and P3. We know P4 is given as 2.5. P3 is already specified, let's say 2.11 bar. And T3 we need to consider in the correct units. When you are dealing with ideal gas law, ensure that these units are in Kelvin. Hi, good evening. Just to give you a quick glance, so I'm just going through a problem, so you can go through the problem once. Maybe I can quickly give it a shot again. So basically you have a closed container. It has a two-phase mixture inside, liquid plus water, and then you are continuously heating it. As it gets heated, the liquid gets converted to vapor. So you are required to find the temperature and the amount of mass vapor that is present inside the container if the final pressure is 1.5 bar. The next part of the question asks you, if the heating continues and all of the liquid is converted into vapor, what would be the final pressure? This is basically the question. Yeah, you have something to say? I guess not. Okay, so I'll keep going. Yeah, so my T3 is the temperature at this particular point before reaching when it is in the fully saturated state. So when it is in fully saturated state, I get that value from the steam tables. So you go to the pressure table and you know what the final pressure is. So the final pressure is around 2.1 bar, or since it is in this particular case, I'll add a value here for the temperature also. So at 2 bar the temperature is given as 120.2 and 127.4. And you are required to find the temperature at this particular point, so you can directly calculate that as a weighted average of these two, so that is 120.2 plus so how do I calculate the approximate value? So I'm just taking a linear interpolation between these two values, so between 120.2 and 127.4 based on the values of my specific volume for the saturated vapor stage. So it is 120.2 plus, you take average between these two, so 127.4 minus 120.2 times you calculate in terms of you have something to say? So that gives me a temperature of around 121.84 Celsius. So with this temperature, so using this temperature I will be able to calculate the final temperature. So I'll just convert this into Kelvin. So I have around 121.84 plus around we need to convert it to Kelvin, that is around 394.84. So how do I find T4? It's straightforward. So I will just calculate T4. T4 is essentially P4 times T3 divided by P3. So this is how you find the final temperature. So now you can also look this up from the superheated steam tables, which we will not go to. So are there any questions in this? I hope not. So we'll go to the next part. Okay, we'll go to the next question. So here you have an insulated tank having a certain volume that is fixed as around 0.25 cubic meter containing saturated water vapor. So it has only vapor at 100 degrees Celsius. The water is rapidly stirred until the final pressure is 1.5 bar. Determine the temperature at the final state and work during the process. So how do you start with these problems? Okay, there are two parts for these kinds of questions. The first one is evaluating the properties like temperature, pressure, whatever they ask. And the second one is when they ask you work done or something else, then you resort to the first law. So first let us focus on how do you determine the property. How do I determine the property? I know the volume, I know initial volume, I know initial temperature, I know the final pressure, and I know that what else do I know? How do I calculate the final temperature? So again we resort to the steam tables. So we know initially that it is a saturated vapor. So from there we will calculate what is the specific volume. We know that since it is a closed tank, the mass is remaining constant. So if volume and mass are remaining constant, then specific volume will also remain constant. So what we do is we calculate the specific volume at the initial state, and this specific volume is going to remain same for the final state also. So now at the final state we have pressure and specific volume. So from that we will be able to calculate the temperature. So this is what we are going to do. So initially volume is specified, the temperature and vapor fraction are given. So from the steam tables, so now I need to look at like temperature and quality are given. So I look at the steam tables from a temperature point of view. So now if you see the steam tables, temperature table, now we need to look at 100 degrees Celsius. At 100 degrees Celsius, you have the specific volume to be 1.673. This is the value I am going to be using. So that is 1.673. And this is the internal energy, and finally the pressure is given. Since it is a closed and sealed container, as we discussed before, the specific volume is going to remain constant. Now at this particular pressure at 1.5 bar and 1.673, so now if I look at 1.5 bar, now if you look at the pressure table, at 1.5 bar my specific volume is 1.159, but the specific volume currently is 1.673, which means the specific volume of the current state is actually greater than the specific volume at the saturated state, which means I am actually in the superheated state. If you are not comfortable this way, you can also think of it like if you try to calculate the vapor fraction using this particular value of specific volume, then you would end up with a value greater than 1, which means you are again in a superheated state. Now if you are in superheated state, now you need to look up the superheated tables, and we need to interpolate accordingly. Now if I go to superheated tables, and then I know my final pressure, so I'll directly go to the pressure one. So this is a superheated steam table at a pressure of 1.5 bar. So at this you have several different temperatures. I need to find the correct temperature. What do I know? I know the specific volume. So using the specific volume, I will find the corresponding temperature. So I'll just do a linear interpolation again. So I am considering these three specific volumes, like at 240, 280, because these are the values that are given in the table. So at 240 specific volume and 280 the specific volumes are given. So I'll just take those values, and I need to find the temperature at which the specific volume is 1.673. Accordingly, I also find the internal energy, that is the secondary. So how do I find this? Again, we do a linear interpolation between these 2 points using these two specific volumes. If I do this, I get a value of around 272.96. I also find the internal energy, which we will be using later for the work done part. Now here it is said that it is a well insulated tank. So if you want to apply first law, when it is a well insulated tank, the net heat interaction across the boundary is 0. So if you apply first law, since the heat interaction is 0, whatever is the work done by this particular stirrer should actually be converted into internal energy of this particular vapor system, liquid plus vapor system. So the entire work done will be converted into internal energy. So if I know internal energy is again a state function, so it only depends on the final and initial states. So I know what is my final internal energy, I know what is my internal energy initially, which I already know from the steam table. So I just do a difference of this, then I get the change in specific internal energy. If I multiply with the mass of the total water plus liquid plus vapor inside the container, I would be able to calculate the total change in internal energy, which is equal to the total work done. For that, I need to determine the total mass of it. So I was given the total volume, and I calculated the specific volume previously from steam table. So using the specific volume relation, I'll be able to directly calculate the mass of it. So if you just do it math, so del Q is 0, PU plus PLW. In this particular case, del W is going to be negative because this is work is done on the system. So if you just substitute the values, you get a value of 139 kilojoule. Are there any queries? I guess it's clear. So we'll go to the next problem. The next one is also a straightforward problem. This also helps you to understand how to use the steam tables. So there is a piston cylinder assembly. It undergoes two processes from an initial state of 10 bar pressure and 400 Celsius. First part is it is cooled as it is compressed at a constant pressure of 10 bar to a saturated vapor state. So initial 10 bar 400 is in the superheated state. What you do, you continuously reduce the temperature by cooling it at a constant pressure till you come to saturated vapor state. So 2 is, so let's put it, 1 is a superheated state, 2 is saturated vapor state, and what is 3? The water is cooled at constant volume to 150 Celsius. So this will be somewhere in the intermediate one, let's say 2-phase region, or it could be subcooled region, which we don't know, which will determine. So the processes are clear. So all you require to find now is you need to determine the total work done and heat transfer in these processes. So whatever these processes are, like the first one is a constant pressure cooling, and the second one is also constant volume cooling. So how do you go ahead with this? So again, you need to determine the properties first, and then you will use the first law to determine the work done and heat transfers. So let's do the property calculation. So initial conditions are 10 bar and 400 degrees Celsius. So this is definitely in superheated state. So I'll just go to the superheated table. I'll check for the 10 bar pressure. At 10 bar pressure, I know the temperature is 400 Celsius. So at this, I'll pick these values up. I've just written them down here. So this is my specific volume, specific internal energy and specific enthalpy. And from 1 to 2, it's a constant pressure cooling, so P2 equals to P1. And I know that the final state is on the saturated vapor line. So my vapor fraction is going to be 1. So now again, I'll go to the steam tables, but now I will look at a 10 bar pressure. So I'll go to steam tables, pressure table, because pressure is known to be 10 bar. So I look up the value of 10 bar. At 10 bar, these are the values that are given. I'll take these values. So I've taken the values at 10 bar as U, H and V is a specific volume. Again, from 2 to 3, it is a constant volume process and mass is also constant, so specific volume is remaining constant. So we know the final temperature as 150 and V3 equals to V2, which is already calculated from before. Now we need to look again the steam tables. Now however, temperature is specified here, so I will look up the steam table for tabulated as temperature. So I'll go to temperature tables. This is the temperature table. I look up the value of around 150 Celsius. So I'll take the values from here. This is the pressure. I'll take this all these values. So I got the values Vf, Vg and other properties. Now it is in the two-phase region. Like if you observe, the saturated vapor specific volume is 0.39. However, the specific volume has to be 0.1944. So it is in the two-phase region. So I calculate the vapor fraction. Vapor fraction is V minus V saturated liquid by gas minus liquid, vapor minus liquid. That is giving me a value of around 0.49. So from there, using this vapor fraction, I'll do a linear interpolation to calculate the appropriate U and H values, which already I got. Now I need to determine the work done as well as the heat transfer. Now for this work done part, how do I do the work done? So work done is again dependent on the path in which the process is happening, or essentially it is a path function, so you need to know the process. So the first one is a constant pressure process, the second one is a constant volume process. So maybe even before going to work done, heat transfer is straightforward, or we will do the work done part. So we just substitute the formula from 1 to 2, it's a constant pressure process, so we just take P times V2 minus V1. This just 100 is just to convert from joule to kilojoule. And similarly for 2 to 3 is a constant volume process, so your work done is 0. So the net work done is the summation of these two. Again for the heat transfer, you need to determine the net change in internal energy, like if you use the first graph, so it is del W plus du. So del W I already have from the previous case, and du is again u2 minus u1. u2 and u1 properties we've already calculated before, so it's a straightforward substitution that you need to do. Okay. Are there any questions? Okay, I think it's clear. So we'll move on to the next problem. It is on mixture of gases. Since your assignments deals with such questions, so I just kept this question. So you have a vessel of a certain volume, 0.35 cubic meter, and it contains a 0.4 kilogram of carbon monoxide and 1 kilogram of air at 20 Celsius. You need to calculate the partial pressure of each of the constituents and the total pressure in the vessel. So you can assume air to be a mixture of oxygen and nitrogen, like 23.3 and 76.7% respectively. All the molecular weights are given. So I have just written down the given information. The total volume is specified, CO and air masses are specified, temperature is also given. I'm just using in the Kelvin so that when you use ideal gas law it will be consistent there. Mass of oxygen is specified to be 23.3% of the total mass of air. So again there will be again two different scenarios that you might have to consider. Whenever you specify these percentages, you could either specify it as a volumetric or a gravimetric. So gravimetric is something based on masses or weights, and volumetric is something based on volumes. So in this question it's clearly specified that it is a gravimetric analysis. So you will be doing it, the 23.3% is out of the total mass of air. So you got the mass of air is given as 1 kilogram, so it will be just 0.233 and 0.767. Universal gas constant be consistent with the units. This is 8.314 joule per mole per Kelvin. You need to convert it into the appropriate units before using it in the energy calculations, because we are dealing with kilograms and grams usually, so this is not the appropriate unit. So we need to use the appropriate molecular weight to convert it into the R value that we typically use in our equations. Okay, now coming to the first part, how do you determine the partial pressures? So how to get this partial pressure? So what is a partial pressure? Now all of these gases are inside the container. So each one of the total pressure is something that we can maintain at say 1 bar. So out of this 1 bar, each gas will have a certain contribution to the total pressure, and that is what we are calling partial pressures. And this partial pressure will be proportional to, from Dalton's law, it will be proportional to the mole fraction of that particular gas. So all we need to determine is the mole fraction. So how do I calculate that? So for each constituent, we have the partial pressure given by Mi times ROT by MIM. So indirectly this is proportional. You can use your normal gas law. So this little mi by capital Mi is your number of moles times nRT by V, where R is your universal gas constant. This is in joule per mole per Kelvin. So for oxygen, you can calculate oxygen by corresponding mass of oxygen, and similarly you calculate for each one of them. So you know the temperature, you know the volume. Now since it is a container and gas occupies the entire container that it is present in, so the volume is specified as 0.35 cubic meters. So the entire volume is something that you need to be using here. The V here stands for the total volume, because each gas, if you are familiar with ideal gas law, it assumes that each of these particles behaves as if it is as if the other gas particles were not present. So they will occupy the entire volume. So you should not actually multiply this with the corresponding mole fraction and use some other value here. So be consistent, use the total volume of the container here. So from this we calculated the partial pressures. Now total pressure is, from Dalton's law, is summation of all these pressures. If I just add up all of this, so I get a pressure of around 3.4 bar. It's a straightforward problem. Now there could be other variants to the problem where they might be asking you, like instead of gravimetric analysis, they might ask you based on a volumetric analysis where these ratios are given, or some, maybe we will take up a problem on that as well. But that is one variation that you could expect. Okay, is this clear? Okay, I guess it's clear. Let's go to the next problem. Again, this is a gravimetric analysis. Just note this fact that whenever gravimetric is there, it means it's on a mass basis, and the data is as follows. So you consider air, and you need to find the gas constant for the air. Note, whenever we say gas constant, we mean in appropriate units as, or maybe I'll write it as joule per kg Kelvin, and apparent molecular weight. Since it's a mixture, you do not have the direct molecular weight, but if you consider the mixture to be a uniform, it's like if you want to consider this mixture as if it were a gas with a constant molecular weight and gas constant, so what would that be? That is your apparent molecular weight. So you just take the values, these are the fractions that are given, and these are the corresponding molecular weights. So how do you determine gas constant? Gas constant is essentially just take the average value, but then the average will be based on some weightages, and these weightages are proportional to the mole fractions that are present in your particular mixture. So essentially you calculate the gas constants for each of these gases, which is basically R naught is with respect to joule per mole per Kelvin. I just divide it with the molecular weight so that you get it in terms of joule per kg Kelvin, and once you get that, you just do a weight average of it, where the weightage is based on the mole fractions. Weightage is based on the mass fractions. Again, coming back to here, so here R is in terms of joule per kg per Kelvin. So since it is in this particular unit, I am doing this weightage with respect to mass fractions. If however it was the universal gas constant, if you were directly using the universal gas constant, then you would be using the mole fractions. Essentially the formula turns out to be the same. If you use a mole fraction here and take the appropriate R value is going to be constant, so if you just consider the mole fractions, this will be multiplied with those corresponding ratios. So but for this problem you can just assume that there is no assumption as such. So you just convert from joule per mole per Kelvin to appropriate units, which is joule per kg per Kelvin, and then multiply with the corresponding weightage factors, which are mass fractions. That gives you the gas constant. Now how do you find the apparent molecular weight? You have what is this universal gas constant. So basically as the name suggests, it should be a universal gas constant. So for that constant to be a constant, all you need to do is your molecular mass should be such that this R naught value remains constant. So whatever R you calculated in the previous step times the apparent molecular weight should give you this particular value. So the apparent molecular weight turns out to be 28.953 or basically 28.9. So this is something that you consider for the air normally. You consider this as a molecular weight for the air, and you can use this as a gas constant for the air. You can remember these values, or if not, usually they will be provided. You can also try it as an exercise. So instead of considering all this one, if you would have considered only nitrogen, which is around 75%, its molecular weight is around 28. So you can assume basically the entire air to be just nitrogen, and you're off with only like 0.9 difference here in the molecular weight. And accordingly you can find the value of R. It turns out that if you just use nitrogen, this value comes out to be around 297 or something instead of 287. So the errors are like within 10%. Okay, is this clear? Yeah, I hope it's clear. So we'll go to the next problem. Yeah, so now instead of a gravimetric analysis, we now have a volumetric analysis here. So what do you mean by a volume ratio of 2:1? So if you have a container, so can I say that inside the container, the 2/3 of its the volume of hydrogen to oxygen is 2:1? Can I say that if the volume of container is 1 cubic meter, so hydrogen is around 2/3 of the cubic meter and oxygen is on 1/3 of it? Just before we discuss that, that is something that will not happen. Hydrogen and oxygen, both of these gases will behave as if the other one is not present, and they will tend to occupy the entire volume. So if these are present inside a container which is of volume 1 cubic meter, then volume of hydrogen is also 1 and volume of oxygen is also 1. It's only the pressures where you find that they will have partial pressures. So what do you mean by 2:1 volume? It's like if I take 2 cubic meter of hydrogen and 1 cubic meter of oxygen and mix them inside a container such that the pressure remains a constant. So when you say something like a ratio with respect to volume, then you need to specify what is the pressure at which these ratios are considered. So it is specified here that the pressure and temperature are 1 bar and 25 Celsius respectively, and if this is the case, you need to determine the mass of oxygen required. So essentially, for example, for 1 kg of hydrogen, what is the amount of oxygen that you would require so that you would maintain this ratio 2:1 at 1 bar pressure and 25 Celsius. So this is exactly how you specify the state. So how do you go ahead with this problem? So all you need to do is assume some particular mass of oxygen. It's like hydrogen mass is fixed at 1 kilogram. So for 1 kilogram of hydrogen, I can use ideal gas law. I know the pressure, I know the temperature, I know the mass of hydrogen, so I can calculate what is the volume of hydrogen. So I know the volume ratio. From this ratio, I will determine the volume of oxygen. So it goes like this. So roughly, the workflow goes like first you assume hydrogen has 1 kilogram. And from there you determine use ideal gas law. To determine the volume of hydrogen, use the volume ratio, which is 2:1, to calculate the volume of oxygen. And once you know the volume of oxygen, you again use ideal gas law. determine the mass of oxygen. So it's straightforward. Maybe you can take a couple of minutes to solve this. Yeah, I guess you would have done by now. So these are the initial pressure and temperature. I will just calculate the mole fractions, and these are the molecular weights of hydrogen and oxygen respectively, so that you can calculate the number of moles. So volume ratio will be equal to mole ratio, so we have directly taken those values. So assuming we have total of 1 mole mixture, all you need to calculate is this particular ratio. So if you just do the math, so it turns out to be around 8. So for every 1 kilogram of hydrogen, you require around 8 kilograms of oxygen, so that you would have a volume ratio of 2:1 at 1 bar pressure and 25 Celsius. Yeah, I guess there are no questions, so we can proceed to the next problem. Okay. This is again one of those problems that we were close to something in reality. So you have an engine cylinder, and that has certain amount of a gas. The gas has CO2, oxygen and nitrogen. So the percentage of CO2 is 12.5 oxygen and 74.5 nitrogen. And this particular thing is actually expanding. It is beginning at around 950 Celsius, and it expands reversibly. So when we are saying reversibly, I think we'll discuss this at length in the next week sessions. And the volume ratio is given as 8:1. So this is expanding. So initial to the final volume is around 8. Final to the initial volume is 8. And according to, so you are going certain process. The process is given by PV to the power 1.2 equal to constant. Calculate per kg per unit mass of gas. What is the work done and what is the heat transfer? I'll just put heat transfer here. The values of Cp, the specific heat capacity at constant pressure, are given as so and so. So these are the specific heats that are given. Okay, how do you start with this? It's again straightforward in this particular problem. So you already know PV to the power n equal to constant, so it is a polytropic process. So what's the work done in a polytropic process? So we use the equation for the work done in a polytropic process. If we want to use that equation, what do we need? So all of this information is already given, but to determine this work and heat transfer, we need to know the specific heat capacities of the mixture. So now we have 3 different components inside, three different constituents inside this mixture. All we need to know is assume that only one component is present. So what would be the equivalent properties of that one component, so that your work done and heat transfer would be same, even if one component is replaced with 3 of these components. So how would I determine those equivalent properties, like the specific heat capacities of this mixture? So the equivalent specific heat, we have something called adiabatic mixing. So if there is an adiabatic mixing, you assume something like this, where your total specific heat will be a weighted average of the individual component specific heats. So what do I mean by adiabatic mixing? So it means that whenever these constituents are mixing with each other, there is no net, like if you consider all 3 of them to be one system, then there is no heat interaction with that particular system across the boundary. So it is as if saying there are no endothermic or exothermic chemical reactions that are happening when this mixing is happening, so that the total energy remains constant. So then if you use that assumption, then you can calculate the total specific heat to be a weighted average of individual specific heats, so which is given by this equation. So this is the total Cp. Now I know the value of R0, universal gas constant. So again, if you follow the same relation, same equation that we did before, so all I need to know is R0, I have to multiply with the appropriate mole fractions to just convert this into the R value in terms of joule per kg Kelvin and then divide it with the total mass so that I will get the equivalent value of R. So now previously carbon dioxide was low, so we got this value around 287. Now because of a higher concentration of CO2, this value got reduced. Because the CO2 molecular weight is higher, so your R value, the molecular weight actually increases, which reduces the gas constant value. And we already know Cp minus Cv is R. So we know Cp, we know R, so from there we calculate Cv. Cv is given by Cp minus R. So I have the values of Cp, Cv and R. So now I need to determine the work done. So work done for a polytropic process we already know is P2V2 minus P1V1 by 1 minus N. In this particular case N is 1.2 and it follows ideal gas law, so PV equal to RT. So basically this V is specific volume. So the mass is already taken into account and R is for that particular mixture that we are considering, so it is already taken care of, so it will be in joule per kg Kelvin. So if I substitute those values, so it will be R times T2 minus T1 by 1 minus N. Now I need to determine T21. So what is T1? Initially it is at temperature of 950 Celsius, but I don't know what is the final temperature. So this is where I need to use the process equation. So I know the process is PV to the power n equal to constant. If I use ideal gas law in this, so I get something like PV to the power n minus 1 equal to constant. So that gives me T1 V1 to the power n minus 1 is T2 V to the power n minus 1. And I know R is the expansion ratio, that is V2 by V1, and that is given as 8. So if I substitute here, so my final temperature is T1 by R to the power n minus 1. So that gives me around 806 Kelvin. Now the question here is, if the process, if we assume that this particular process is adiabatic, so instead of any heat transfer, if it was adiabatic, then your gamma would actually be different. So in this case of an adiabatic process, which we will discuss later, in the special case that it is reversible, like the one here mentioned in this particular question, a reversible and adiabatic process leads us to an isentropic process, which is for which the process equation is given by PV to the power gamma equal to constant. So yeah, your n will be equal to gamma, which in this case you can consider to be 1.3. So what would you expect? So if suppose if n is replaced from 1.2 to 1.3, so will your temperature drop be higher or lower than the present case? So for example, if it was adiabatic, do you think the temperature would be lower than this 806 Kelvin or higher than this? We will calculate that as well. So I'll leave that as an exercise, or we'll discuss it right now a little later. So what is the heat transfer? So you calculate the internal energy change, that is Cv times T2 minus T1. Just substitute that into your first law, that is Q equals U plus W, so you get a total value of around 190. So what is happening here? So if suppose, so when you are using an IC engine, so you in order to expand this piston, in order to push the piston, you need to do some work on it. So obviously the work is done by where is the work getting done? So there is some combustion that is happening inside, which is actually giving the energy to do this particular work. So this is the total amount of work, and this is a change in internal energy that is happening during the expansion process. So if this Q would have been 0, all of this would be converted into your internal energy change, which means your delta T will actually be much higher in case of an adiabatic process. So what is happening because of this heat transfer is that is low in this because of this heat transfer, your delta T is actually getting reduced and you are actually experiencing a much higher temperature. So instead of this polytropic process, if it were an adiabatic process, then this temperature instead of 800, it might be close to say 600 or somewhere between 600 and 650 Kelvin. So then your internal energy change will actually be enough to compensate for this 190 kilojoule per kg that is happening. I hope this is clear. Are there any questions? I guess there are no questions, so we'll go to the next problem. So there is a certain quantity of steam at 10 bar pressure and 0.85 vapor fraction. It occupies 0.15 cubic meter. Determine the heat supplied to raise the temperature of the steam to 300 Celsius at constant pressure, and how much of this heat can appear as external work. It says that you can use the specific heat of superheated steam as 2.2 kilojoule per kg Kelvin. So you can also use this particular value, or you can refer to your steam tables and then take the approximate value from there. So for now, for this problem, we'll stick to this particular value that is given here. Okay, so initial pressure and vapor fraction are given. So I'll go to the steam table and determine what is the specific volume for this particular value of Reynolds fraction, and then I can calculate the volume is given, so I can indirectly from there I will be able to directly calculate the total mass of steam that is present initially, and the final temperature is given to be 300 Celsius, and it is specified that it is happening at a constant pressure process. So you know the pressure to be 10 bar, at 10 bar 300 degrees Celsius. So is it going to be superheated, or is it going to be with inside the two phase? So how do you know that? You just go to the steam table, check the pressure table. This is a temperature table. You check the pressure table, you go to 10 bar pressure, and you see the temperature over there. At 10 bar, your saturated temperature is 179.9. So anything above this temperature, you will be in the superheated region. So it is saying that at 10 bar, you are reaching a temperature of around 300 Celsius, which means it is going to be in superheated state. So you go to the superheated steam table, you look up 10 bar and 300 degrees Celsius. Okay, you can just take a linear interpolation to determine the corresponding values of other properties. Okay, let's get this. So initial pressure intervals and P2 is given to be P1. So the first one is you determine the properties. So initial temperature is the saturated temperature at 10 bar pressure, which is 179.9. The saturated liquid and saturated vapor specific volumes and other values you have taken from there, from which you can calculate the specific volume as using this particular relation. The total mass should remain constant during the process. You are assuming that the mass is constant, is not leaving the system, from which you get the mass to be 0.9068 kilograms, and the heat transfer and work done. So what is a net heat transfer? So how do you calculate that? So what is happening inside the cylinder? So initially you are at 179.9 with the vapor fraction of 0.85. So there is some liquid plus vapor. So what you are doing is you are heating it up. So the liquid is getting converted into vapor at constant pressure, and then once it gets converted into vapor, in the vapor state you are again heating it up to 300 degrees Celsius. So there are two things that are happening. One is the liquid part getting converted into vapor. So all I am doing is taking the fraction of the liquid and multiplying it with the latent heat of water, which is essentially Hg minus Hf. So from the liquid, saturated liquid to saturated vapor, this is the total amount of it, out of which only this portion is the liquid one, and the entire portion, once converted into vapor, it should move from T1, that is a saturated vapor state, to T2, which is a final superheated state. So I am using the Cp value that is given to me in the problem here. If I substitute the values and then I just use the mass that I have calculated here before, so multiply with this specific heat, so I get the total amount of heat transfer. So internal energy is again a point function. You just need to determine what are the initial and final values, and from there you'll be able to calculate the work done, or you can also calculate the work done directly using this particular one. At constant pressure, it is heated till the temperature is 300, which means you can directly use P times V2 minus V1. So how do you determine V2 and V1? Again, we use the ideal gas law. So if you use the ideal gas law, so V is proportional to T, so V1 by T1 is V2 by T2. So V2 is V1. So essentially, initially the V1 is actually different. So this V1, V1 is the initial state. So the initial state is what we are, it's not with the vapor fraction. So this law can be used only in the superheated, okay, this should be superheated region, in the superheated state. So within the superheated state, I calculate my total final specific volume as the initial specific volume times the ratios of these temperature increases, so which gives me a value of V2 here. and mass is constant, so the final volume I'll calculate from this, so which may not be required. You can directly multiply with the mass and you can directly calculate the percentage of heat. Like once you calculate the work done, that is P times, since it's a constant pressure process, it's going to be P times V2 minus V1. This 100 is just to account for the unit, like I'm just converting from joule per kg to kilojoule per kg. Like since pressure P is something that I've considered in bar, and then I have the fraction of heat that is converted to work, we just divide W by Q times 100, so that is giving around 14%. So out of the total amount of heat, only 14% is actually converted into external work at a constant pressure process. If it were a constant volume process, then it would have been 0. Okay, now that we are halfway into the session, so I would like to pause for a time of like a couple of minutes. So if you have any questions, we can discuss them. Okay, I hope there are no questions. We'll move on to the next couple of problems and then we'll wind up for today. So we have, to see this problem, you have two boilers, one with a superheater and other without a superheater. They are delivering equal quantities of steam into a common main. The pressure in the boilers and the main, so all of them are at the same pressure, 20 bar. The temperature of the steam from a boiler with a superheater is 350 Celsius, and say without the superheater, you assume that it is in a two-phase region, so you will assume that it is going to be at a temperature which is corresponding to the saturated temperature of 20 bar pressure, and the temperature of the steam inside the main is 250 Celsius. Determine the quality of the steam supplied by the other boiler. So basically you have two boilers, one of them is in superheated state, the other one is somewhere in the two-phase region. So you need to find the quality of steam inside the two-phase region such that your final temperature inside the main after mixing both these boilers is going to be 250 Celsius. Again, all you need to do is first determine the properties for boiler 1, boiler 2, main, and then in order to determine the quality of steam boiler 2, all you do is an energy balance. You just do an energy balance so that there is like when you consider all these three together as your system, so the two boilers plus the main as your system, there is no net heat inside or outside of that. So the net heat interaction will be 0. So whatever heat that is coming in from boiler 1 and boiler 2 should be something that is being consumed by the main. So that is the last part. So for boiler 1, how will it determine the properties? Initial the pressure is given, temperature is given, and specific heat capacity is also given. So from steam tables at 20 bar pressure, and this particular the saturated temperature is 212, which is obviously means this is a superheated station, that you can also directly get from the name itself, that it says that this boiler has a superheater. So superheating temperature is also given as T1. So from this, so how do I calculate the enthalpy at the superheated state? So I know my initial temperature. So all I need to do is, from the first thing is to determine the total enthalpy. I need to consider the enthalpy at the gas state, plus your temperature is changing from the saturated state to the superheated state, multiplied with the specific heat. So your enthalpy is defined in this particular way. So so your specific heat is essentially dH by dt. So dH is H1 minus Hg1, and dt is T superheated minus T saturated. So from there you can calculate the enthalpy for the first boiler. Now similarly for the second one, in order to calculate for the second one, you need to know the actual quality, which is something we do not know. So what do? So T2 is something that is unknown, but since it does not have a superheater, we assume that it is going to be somewhere inside the liquid dome. So the H2 is going to be HF2 plus X2 times H2 minus HF2. But X2 is something that we do not know, that is unknown, that we are trying to find in the problem. So they ask you to find the quality. Inside the main, we know the final temperature is 250 Celsius and the pressure is 20 bar. So as we've seen before, the saturated temperature at 20 bar is 212. So this 250 is greater than that, which means again you are in the superheated region. So your enthalpy is going to be the gaseous enthalpy that you calculate, the enthalpy of the vapor state, plus Cp times delta T. Delta T here, instead of from the saturated temperature to the main temperature, which is 250 Celsius. So this is the H main. So all you have to do is an energy balance. So m dot 1 H1 plus m dot 2 H2 is going to be m dot main H main. So what is m dot main? So if you consider unit mass of steam coming from each boiler, then the mass that is inside the main is going to be 2 times of it, because there is 2 inputs. So H1 plus H2 is going to be 2 times H main. So my equation that I am going to solve is 2H main minus H1 minus H2. This needs to be 0. So if I solve that equation, I am getting the value of X to be around 0.9. So this is the vapor fraction of the liquid vapor phase inside the boiler tube. So this is a straightforward question. Are there any doubts in this? Okay, I guess there are no questions. Okay, then we'll go to the next problem. So I would like to leave a little exercise for this problem. I'll just glance through the solution, but then I would expect you to go through it, and then maybe you could come up with any questions, then we'll discuss. So there is a piston cylinder that has the 3 kg of wet steam, which means the Reynolds fraction is not equal to 1 at a certain pressure. The initial volume is specified. Now the steam is heated until its temperature reaches 400 Celsius. The piston can either move up or down unless it reaches the stops at the top. So there is a specific volume. So initial volume is 2.25. Now it gradually rises and then it hits the stops. Once it hits the stops, then the volume cannot increase. When the piston is up against the stop, the cylinder volume is 4.65. So this is the maximum volume that it can expand to. Determine the amount of work and heat transfer to or from the system. So how do I go ahead with this problem? So there are 3 states. So initial pressure, volume are given, mass is given, so I can calculate the specific volume. So initially, as the piston is moving upwards, before hitting the stops, the pressure is constant. So assume a constant pressure process, and from there you can calculate the properties. And once it hits the stops, then it is a constant volume process. So this 400 Celsius is the temperature until the steam is heated until its temperature reaches 400 Celsius. So if you do the properties, the initial state I just divided into 3 states. So for the state 1, how do I get the properties? State 1 is a pressure of 1.4 bar and a specific volume of 0.75. and T3 is the final state, that is at 400 Celsius and volume of 4.65 cubic meter. I know the mass of is 3 kg, so this is the final specific volume. Or yeah, V2 and V3 is equal to V2. So how do I calculate the state 1? My initial pressure is given, initial specific volume is given. So I look up the steam tables. Like pressure is given, so I should look up the pressure table. So I go to the pressure table and I need to find the value of 1.4 bar. But here I am given only 1 and 1.5 bar pressure here. So I just take these values and then take a linear interpolation between these two. Yeah, okay. So we have two different pressures. 1 bar, we have these are the values taken from the steam table. At 1.5 bar, I have the values taken from the steam table. So I need to determine all these values at 1.4 bar. So now the question again is you just do a linear interpolation and then you determine all these values. And once you get the values, you need to determine the vapor fraction. So vapor fraction is again V minus liquid by vapor minus liquid, that gives me around 0.59. So once I get the value of vapor fraction, I can calculate enthalpy, internal energy, everything else using the appropriate relations. So this is straightforward. Now for the state 2, from state 1 to state 2, it is a constant pressure process, and so we just have P2 equal to P1, and we know the final specific volume, so we know final pressure and final volume. So at this particular value, we calculate the saturated temperature, that is coming to around 109.046. So the question is, how do I know whether it is in a vapor state, or like how do I calculate this temperature? This is again from a linear combination from above that I have here. So at 1 and 1.5, the saturated temperatures are given. So using a linear interpolation, I will calculate the value of saturated temperature at 1.4 bar. So that is 99.63 plus 0.8 is basically 1.4 minus 1 by 1.5 minus 1 times your temperature difference, that is giving me a value of around 109 Celsius. So now I already know that Vg is going to be Vg1. At 1.4 bar, if we see the vapor pressure and compare it with the specific volume that I want, we know that 1.5, so if we just have a look at it, so the value of Vg is around 1.266. So this is the value of specific volume of the vapor at 1.4 bar. But the value that I would require is 1.55, which means since 1.22 is 1.26 is less than 1.55, which means I am in the superheated region, which means gas is actually occupying a larger volume than what it has to be in a vapor state. So you are in a superheated region. So now you go to superheated steam tables. Here comes a little bit of more approximations that you need to do. Like nowadays you are already given, like you already find most of the tools available online. So you directly type in the pressure and temperature and it will give you the property values. If they are not provided, then you have to accordingly look up the tables. So for example, here you can look up the superheated steam table. You know the pressure is 1.4 bar and specific volume is 1.55. So if you go to superheated steam table, so you have only two values here. You have a pressure of 1 bar and 1.5 bar, and you don't know which values to use because you need to determine the final temperature. So how do I do this? You need to do two linear interpolations. So the first thing, I know that specific volume is close to 1.55, so which is a value somewhere here or somewhere here near 240. So the first thing I'll do is I'll do a linear interpolation across temperatures. So that is something like this. So you assume a constant temperature at 240 Celsius. I'll consider a superheated table at 1 bar and 1.5 bar and then do a linear interpolation to get the specific volume at this particular 1.4 bar, which I got a value of around 1.728. Similarly I do for the other values. Once I get these values at 240 Celsius, now I need to I will use them to actually determine at 1.4 bar and 1.55 meter cube per kg what is the corresponding temperature. So this is something that I need to determine. So I'll just wait for a minute so that this thing actually goes inside. So if there are any questions you can ask. So why am I doing two linear interpolations here? So what is given and what is required? I need to find what is the temperature at which I will have a specific volume of 1.55 meter cube per kg and I will have a pressure of 1.4 bar. I need to satisfy both of this. So what am I doing? So ideally you require at 1.4 bar, I'll take a specific volume of 1.266. Like we know this from the saturated table. These values are taken from the at the saturated vapor state, and these are the values are required to find. I know at 1.4 bar and 1.55 what is the temperature, internal energy, enthalpy, specific internal energy, and what are the other properties that you need to find. But then in order to do a linear interpolation, I would also require to find a third state. This third state should also be at the same pressure as the other two states, so that I can do a interpolation only on the specific volume. But how do I decide which third state to use? So to do that, what I have done is I have considered again two different superheated states, one at 1 bar pressure, the other one is at 1.5 bar pressure. Using these two different values, but both of them should be at the same temperature. So I have taken a temperature of around 240 Celsius. From there I calculate an equivalent properties for VU and then use them here. Once I calculate these values, I use them here to populate this particular row. And then I can do a linear interpolation between the first and the third rows to determine the appropriate values of T2, U2 and H2. This is for state 2. Now from state 2 to state 3 is a constant volume process. And I know it is going to be in the superheated state. So I know for the final temperature is already specified as 400 Celsius. So at 400 Celsius, I need to find the correct value of pressure, which is something that I don't know. So what I do, I take two different, so I go to steam table. I know the pressure is going to be somewhere above 1.5, like we already know P2 is 1.4. So if you are heating a gas in a closed space, your pressure is going to increase. So you know the pressure is somewhere above 1.4 bar. So if I go to steam table, the next values are 1.5 and 3. So I take these two values. I know my specific volume has to be somewhere around 1.5. The specific volume has to be constant, which is equal to 1.55. So I go to this table. I see the value that is close to 1.55. So I need to find the corresponding temperature. I know the temperature is 400 Celsius. So at this 400 Celsius, I take the specific volumes accordingly. So at 1.5 bar and 400 Celsius, I have a value of 2.067, and here I have a value of 1.032. So if I just take in those values, and the specific volume I know as 1.55. So whatever is constant is something that I do not have to worry about, because even if I do some linear interpolation, the value is not going to change. So again, from there I calculate this corresponding P3, and all the question marks that are here are obtained by a linear combination, and the linear combination is based on the value of the specific volume. So once I have all these values, energy analysis is straightforward. You need to determine the total Q and work done. So the work done for each of these processes, you calculate Q and U. So Q is H2 minus H1, and then U is U2 minus U1. From there you calculate the work done process. So you don't even have to do all of this. You can directly calculate the net change in internal energy as m times U3 minus U1 and the net heat interaction is this, and from there you can calculate the net work done as Q minus U. You don't even have to do this process by process. I think the question asks you to find the amount of work and heat transfer to or from the steam. So it turns out that the W is positive, which means it is work done by the steam, and Q is also positive, so heat is being added or removed from the system. So as you are continuously heating up, so heat is added to the system, so this turns out to be a positive value, which is correct. And the work done is also by the system, because initially during a constant pressure process, the piston is actually moving upwards. So work is being done by the system on the atmosphere till it reaches the stops, and once it reaches the stop, the volume becomes constant, and from there you do not have any work done. Okay. Are there any questions? Okay, I hope it's clear. So these are the questions I have for this week. So we've discussed around 10 problems. So if you have any queries, I hope, okay, I guess there are no queries. So we can call it a day for this week, and we'll meet next week and we'll solve few more problems. Thanks for joining. So we'll meet next week.